Hi everyone, welcome back to Dave's Math channel. This is my 10th video in a sub-series on derivatives of my series on first year calculus. And today I'm going to talk about a very important rule of differentiation known as the chain rule. This is I think the last big rule we're going to have to do. But anyway, it's a very important rule and it's written out here on the slide and I'll get into it in a minute. Let's begin. So what does a chain rule say? I mean, when do we use it? We use it when we have what is called a composition of two functions. So if we have a function that's f of g of x, where f and g are two different functions, then the chain rule tells us how to differentiate such a function. And you can see if you look on the left, this is the formula in terms of Newton's notation. Looks pretty ugly. So it says the derivative of f of g of x is f prime of g of x. That means you have to first calculate the derivative of f and then use g of x as its argument. And then you still have to multiply that by the derivative of g of x, g prime of x. This is what this formula is saying. And that looks kind of ugly, but there's a much nicer way to write it, and that's in terms of Leibniz notation. So if you just imagine you have two functions here, y is f of t and x is g of t, then a nicer way to write this, we really want to think of y as a function of x. So, f of t, if you substitute g of x for t, you just get t equals g of x, and that gives you what you want. So dy dx, that's the thing we're trying to calculate, y prime of x. And that is just equal to dy dt times dt dx. This just looks like multiplying fractions, which it kind of is in a way, as we'll see. That's how you prove this, actually. So I'm going to present two proofs of the chain rule. And the first proof uses Leibniz notation. And I think this is a big reason why I think most people these days prefer Leibniz notation to Newton's notation. I mean, it makes proofs like this a lot more obvious. If you tried to prove it using Newton's notation, it would be a lot messier. And I'm going to do that after this slide. You'll see it's a lot messier proof. But the proof in terms of Leibniz notation is very simple. So dy dx, if you think of these d's as infinitesimals, which they're supposed to represent. So remember the d of something, df, is like the limit is df goes to, delta f goes to 0 of delta f. So here you can think of dy dx. dy is just a small change, an infinitesimal change of y, and dx similarly is an infinitesimal change of x. And if you think of these both being functions of some third variable t, or u, I guess they're using here, then we can just write dy dx as the limit as delta x goes to 0 of delta y over delta x. But now we can write that as a ratio, delta y over delta u times delta u over delta x, where u is kind of an intermediate variable. And then you know that the limit of a product is the product of two limits. So you can write that as the first one is the limit as delta x goes to 0 of delta y over delta u, and the second one is the limit as delta x goes to 0 of delta u of delta x. So that's just dy du dx. That's one way to write the chain. Here's a more complicated proof. This is in terms of Newton's notation. So if you wanted to prove the chain rule using Newton's notation, you can see it's a lot more messy. And this is actually a more rigorous proof because now we're using the definition of a derivative in terms of limits. We're not just using deltas here. We're being a little more rigorous. So we use the definition. Let's just do it. Y is f of g of x. So dy dx is the limit as h goes to 0 of f of g of x plus h minus f of g of x all over h. Well, that's pretty ugly, but we can simplify it a little bit, actually. And it looks like we're making it more complicated here. But we're multiplying both the numerator and denominator by g of x plus h minus g of x. Why are we doing that? Because remember, this is a limit of a product, which can write as the product of two limits. So let's just skip to the, and we can rearrange things too. So that's what they do on the second line. So let's just swap the denominators. So now we have inside the limit, we have f of g of x plus h minus f of g of x. And now we've replaced h with the other denominator, which is g of x plus h minus g of x. And now we're multiplying that whole thing by g of x plus h minus g of x over h. Well, I think you should recognize the second fraction in this limit is just another derivative. So we have g of x plus, limit as h goes to 0 of g of x plus h minus g of x over h. Well, that is clearly equal to g prime of x. And then what are we left with on the left? We're left with the limit as h goes to 0 of f of g of x plus h minus f of g of x over g of x plus h minus g of x. Well, now if you think of g of x as your new variable, then it's really just f prime of g of x. The thing, this ugly limit on the left, is really nothing but f prime of g of x. So we have f prime of g of x times g prime of x, and we've proven the Newton form. And you can see it's a lot more messy than Leibniz form, but it basically says the same thing. So anyway, now I've just stated and proved the chain rule, but we really want to apply this. I mean, it's a very useful rule, like I said. So I want to finish by going over some examples here. Here's a good example, and you use it all the time in calculus. A lot of times you have, complicated functions that are compositions of other functions, and composite function, if you like. So here's a simple example. Let's compute the derivative of sine of 2x. So 2x is the argument, and you can think of f of x as sine of x, and g of x is just the argument, which is 2x. So now we can apply the chain rule. So, the derivative of sine of 2x is just the derivative of f of g of x, and we can apply the chain rule that says that's equal to f prime of g of x times g prime of x. Well, g prime of x is clearly cosine of x, and f prime is also cosine, so f prime of g of x is going to be cosine, or actually, I'm sorry, g prime of x is 2, and g of x was 2x. G prime of x is 2. So, but now f prime of g of x, that's going to be cosine. Remember, f prime is cosine since f is sine. But then the argument's 2x. G of x is 2x. So we have, on the left, we're going to have cosine of 2x. And now we have to multiply that whole thing by 2. And when we're left with is 2 times cosine of 2x. That's how that works. And number 2 is a little bit more complicated, kind of the same idea. Here, we're doing basically the same thing, except now our g of x is 2x plus 3 instead of 2x, and now our f of x is cosine instead of sine. So same idea. Let's do g prime of x first. So g of x is 2x plus 3. Its derivative is 2, clearly. So we're going to get a factor of 2 on the right when we're done with all this. And then f prime, since f is cosine, f prime is minus sine. But now we have to replace the argument x with g of x, which is 2x plus 3. So in the end, we're going to get sine of 2x plus 3. That's f prime of g of x. It should be minus. I think I'm left out a minus sign. Yeah. Should be minus 2 sine 2x plus 3. Yeah, that's how that works. So I think you kind of get the idea, probably. Let's just do a few more examples. They can get pretty complicated. Let's do another one that's even more complicated. Let's compute the derivative tangent of x squared plus x plus 1. Well, now our f of x is tangent x, and our g of x is x squared plus x plus 1. And so, the derivative of tangent is secant squared. And now we still have to compute. So on the left, we're going to get secant squared of x squared plus x plus 1. That's our f prime of g of x. But we still have to do g prime of x, and that's going to be 2x plus 1. So when we're done, we get 2x plus 1 times the secant squared of x squared plus x plus 1. It's good to see examples. I think the more examples like this you'll see, the more comfortable you'll get with this. This is a little bit of a complicated rule, but like everything else, the more you do it, the more you get used to it. It's kind of like learning to ride a bicycle, I guess. But anyway, let's do another example. How about the derivative cosine of sine of x? Well, here our f of x is cosine x, or g of x is sine x. So derivative of cosine we know is minus sine. So, but then our f prime of g of x is going to be minus sine of x. That's the first term. And then the derivative of sine of x is cosine x. So in the end, we get minus sine of x times cosine x. Kind of nice. And the last example I'm going to show, you actually have to use the chain rule twice. Sometimes you'll have to use it more than once. And this is a good example. Suppose we want to compute the derivative of sine of x. This is a sine composed with itself twice. So anyway, let's just see what we get. So now we want to do this in two steps. So let's first do sine of x, because that's going to be, if we call g of x sine of x, then g prime of x is going to be the derivative of that. We can write g of x as f1 of g1 of x, where f1 and g1 are both sine of x. So when we take that derivative, we're going to get cosine of sine of x. That's our f1 prime of g1 of x. And then we're going to have to multiply that by g1 prime of x, which is cosine of x. So we're going to get cosine of sine of x times cosine of x. That is g prime of x. Now we have everything we need to compute the derivative of the whole thing. So if we let f of x be sine of x and g of x be sine of x, then we can now apply the chain rule, which says the derivative is f prime of g of x times g prime of x. So our f prime is going to be cosine, and our g is sine of sine, so we're going to get cosine of sine of x first, and then our g prime of x is going to be cosine of sine of x times sine of x. We already calculated that. So that's what we get. Cosine of sine of x times cosine of x times cosine of x. Kind of cool. I think you can kind of see the pattern of this. And I think if you compose sine as many times as you want, this pattern would continue. Anyway, that concludes my video for tonight on the chain rule. Thank you for watching, and I'll see you guys next time. Bye.